Hello, and welcome to our first class lecture on the scientific method and a short history of chemistry. So, chemistry is the study of matter, and even before we knew about sciences or anything, people have been trying to understand matter and the world around them. It's been important through all of recorded history. So, prior to calling it a specific science or anything like that, I want to run through some of the major milestones in understanding matter that we've had as the human race. So a very early one was advanced in metallurgy, being able to work with and manipulate metals. This would give people an advantage, make a stronger sword, you have an advantage over your neighbors, you'd be able to defend yourself against wild animals better, etc., etc. So some of those major milestones are bronze artifacts. We've been able to find bronze swords dating back as early as around 4,000 to 5,000 BC, and that's of course is a stronger sword. So it's a stronger metal, able to hold up better in battle than stone tools would, or weaker metals before, like it made out of copper or something like that. And bronze is an alloy of copper with other things, arsenic or tin. Then iron was first been able to be extracted from its ore around 3000 BCE by the Hittites. And that's not necessarily stronger than bronze, but they can make a lot more of it. We're able to make a lot more strong swords from there going forward. It's not as valuable or not as rare as copper is. Then glass. Glass was made since it's at least 3,500 BCE, essentially a purified form of silicon dioxide, which is the same thing as sand. And it became in widespread use by the Roman Empire. And what you see there is a picture of clicked out of the slide. What you see right there is a picture of a glass vessel from the Roman Empire. They like to work with glass a lot, and there's a lot of glass artifacts left from Rome. Soap, you don't think about it, but this is an early advance in chemistry where we have to actually do a chemical reaction to obtain this substance. Was used in Babylon at least as early as 2800 BCE. They found a clay tablet describing the recipe for what things to react to make soap actually in Babylon. So that's pretty cool. Gunpowder was actually invented by ancient doctors, essentially, people trying to make medicines in China. They were trying to mix some herbs and some different things together, and it blew up. And so they said, hey, wait, this might be useful for something else. So they used it. The funny thing about that is actually the first times that gunpowder was used, it was really used unsuccessfully. No one knew how to control it, and it was not a good weapon of war at the time. Both were losing efforts when it was used. But of course, it's come around since and become very, very valuable for us in that way, and destructive in our world, of course. What's amazing is that the ancients had their priorities correct, and they've actually been fermenting sugars into alcohols since at least 10,000 BCE, so way before all of that stuff, with beer coming online around as early as 7,000 BCE, wine around 6,000 BCE. And then in more modern times, only about 1,000 years ago, did we start actually distilling alcohol into the more concentrated, stronger forms of liquor. So that's the sort of ancient lead up to where we are today in the science of chemistry. You don't need to know any of those dates, it's just for informational purposes. But, so moving forward, into the Common Era, into the last 500-600 years or so, we had this science, or not a science, but a thing called alchemy, and it was essentially this magical art. And a lot of times they'd be trying to talk to the spirit world and get some crazy way of mixing up a potion that would do something, or converting lead into gold so that you could do something more valuable, or think Rumpelstiltskin, this idea of how do we convert straw into gold or something like that. So it's this idea of how do we work with the elements, but it didn't take the form of a science or anything like that at that time. Until what happened was the scientific revolution, until all of those old ideas, those old arts like alchemy, which was essentially a magical art at the time, became part under the tent of science and became what's now known as chemistry. So that scientific revolution happened, we really give the credit to this guy, to this guy named Sir Francis Bacon, and it's not really fair. These ideas were first introduced long before him, at least, by Greeks, by the Moors, by different civilizations throughout history. Some of it was in ancient China as well, all over the place. But this guy sort of started in the Western world. He wrote a book called Novum Organum, and he published it in both English, the common language in England, and Latin, the common language of educated people around Europe at the time. And he really started to get everybody on board with this idea of approaching things according to this method that he called science. That's where it comes from. So the scientific method is based on this idea of empiricism. It's a way of knowing about the world based on what we can see and observe and test. And that's different than the ideas that were at work in alchemy, where we might know about the world based on calling upon some spirit to come help us, guide us, and give us special knowledge or something. That we're not going to do it that way anymore. We're going to methodically, slowly go about and learn about the world by observing it and by doing things to test those observations, or test those ideas we have about those observations. So that's been we've had an incredibly successful run with this idea of science since then. And since that time, since 1620 when he wrote that book, we've been making just amazing progress in our understanding of the world through this method that we call the scientific method. It shouldn't be, it starts out, every science class we start talking about it, but it shouldn't be discounted as a small thing. It's taken for granted now because in your lives, science is an understood thing and is an accepted thing in our society. But it wasn't always, and the progress that we've made in the last few hundred years definitely could not have happened without this way of thinking about the world. So the scientific method is actually really simple. Start off by just making observations. Start off by just making some observations. Then, based on what you observe, formulate a hypothesis. Try to understand why that happens. And then all you have to do is go through and test that hypothesis. So if you think it happens for this reason, design an experiment that would test whether that's still true. If you think that butterflies migrate a certain direction, well, at a certain time of year, well, go out and observe. See if they come through. There you go. That's a test for that experiment. If you think mixing one thing with another will explode, well, mix them and see if they explode. That's a test for your hypothesis. And you can keep designing new ways to see if that happens over and over and over and over again, if it always happens. Maybe they explode at room temperature, but if you cool them down, then you mix the same two chemicals and they don't explode. Each one of those new tests helps us understand the world. And eventually we put the result of each test together into what we call a theory. And then we keep refining and keep testing. And that process, little by little by little, with each test, has helped us learn so much amazing stuff about the world. Landing rovers on Mars and driving around Mars, drilling into the surface, finding out information about another planet, all comes as a real result of these incremental tests. Try something else, try something else, try something else. Develop a larger theory. Well, if that works, can we do the next test and the next test and the next test? And so on from there. So it's an amazing idea. Here's a little graphic. Every textbook will have something like this. Basically just start out with your observations here, then find patterns and trends and laws, things that you're always observing to be true. Formulate a hypothesis and test it by designing new experiments and analyze the results of those experiments, and you eventually formulate a theory which encompasses a lot of those ideas and is a more accepted understanding of the world and what happens. So that idea of science in general was put out by Sir Francis Bacon. To apply that to the old idea of alchemy and bring it into the modern era of the science that we call chemistry, this guy named Robert Boyle came along, and he said, well, chemistry is the complex emotional or psychological interaction between people. And that's actually not true at all. That's a different kind of chemistry. Now, he published this book called The Skeptical Chemist in 1661, And in that book, he talked about how you could develop these experimental methods to work with matter, not the way the alchemists did, but to actually do it the scientific way. How can we test this? How can we learn about matter through experimental methods? Just think about the basic stuff that you associate with chemistry right now. Test tubes and beakers. None of that stuff existed back then. So that's what he's pioneering, is this basic, fundamental, how do you work with matter? What kind of equipment do you use? How can you go about designing experiments to test matter, etc.? So from that point, he birthed this field of chemistry. So let's go ahead and actually break in now into some of the discoveries that resulted along the way in studying this field of chemistry. So one of the first thing was, that has happened throughout, is the discovery of specific elements. We already talked about some of that in ancient history. Obviously, people, well before we have a record of it, knew about certain elements like gold, silver, those kind of things. So ancient peoples probably only knew about 9 elements before the 1st century CE. And those were gold, silver, copper, iron, tin, lead, mercury, sulfur, and carbon. And what they knew about the world was essentially about the fundamental part of the world, about the elements that make up all matter, were only about those 9 elements. The rest were around them, but they hadn't isolated them. They didn't know anything about them in particular. So as time progressed, they discovered the next 4: arsenic, antimony, phosphorus, and zinc. Then in the 1700s CE, we picked up even further. We found 19 new elements. Then in the 1800s, we found 52 new elements, and it's progressed from there till today, when we know of 118 different elements. And we lay those out on what's called the periodic table, which tells us something about the properties of each one of those elements. So when we were going through the process of discovering all of these different elements, not much was known about them, just that, gold has different properties of silver, and gold never changes into silver. That's pretty much all people knew about it. So they didn't understand how they worked together, or why one was like another, but it wasn't like something else, any of those things. And there was a lot of work, a lot of discussion back and forth, people trying to understand that. And one guy who was really influential in starting to understand the patterns that were at work within the elements was this guy named Mendeleev. So he's this Russian guy, and the story is that he would write down an element's name and its symbol and everything he knew about the element, its properties, its mass, on a card, and he would take lots of long train rides, and he'd kind of play out these cards in different orders until he kind of found one that started to explain the properties, and that's really the birth of the periodic table. And one of his early ones in 1871 looked like this, and you can see that he's just sort of laying them out in these columns, where he says, well, these ones all have similar properties, and these ones all have similar properties, and these ones all have similar properties. So he's putting them into a common group, and he's trying to understand something about how they work together. And you'll notice sometimes some elements were listed twice because he wasn't really sure. They were kind of like one and kind of like something else, like copper's over here, and it's also over here on this side as well. Because he wasn't really sure. It sort of behaved like these, and it sort of behaved like these other ones at the same time. So he's just trying to figure it out, and this is one of his earliest examples. The modern periodic table looks like this. The groups, the columns, or groups, whichever way you want to think about it as you go down, are elements with similar properties. So that's the basic organization of the periodic table. The smallest element is here, it's element number 1. The biggest element is down here. It's not listed on this table, but it's 118. These ones down here have just been discovered very recently. So it's smallest to biggest, and the properties repeat with each row. So the lithium doesn't have properties of anything in its row, but it starts over, and sodium has the same properties of lithium. So then it goes through, and then potassium has the same properties of sodium and lithium, etc. So we're going to learn tons more about the periodic table, but that's basically it. They're listed in order in groups that all have the same properties. So from there, we started to know that there are these different elements, but no one understood exactly what made gold different than silver. What was it about gold that was different than silver? We knew its properties were different, but we didn't know fundamentally what either thing was. So this is sort of the history of how people started to understand that matter. First, understanding that there were things called atoms that make up that matter, and then understanding what makes up an atom. So it sort of was just these discussions by people. People would do some experiments and say, hey, I think maybe matter's like this. And then someone else would do some experiments and say, nah, I don't think it's quite like that. Maybe it's something else. Excuse me. So a few of the major milestones in that process came from these guys, from Antoine Lavoisier, who came up with the law of conservation of mass, Joseph Proust, who came with the law of definite proportions, and John Dalton, who came up with the law of multiple proportions. And basically, these are just common observations that they made. So Antoine Lavoisier said, in a chemical reaction, matter isn't created or destroyed. So when you mix two things together and you see them react, whatever matter is there, it's not ceasing to exist and it's not coming into existence. It's not magic. Whatever was there, it did some reaction, but it's just changing into a different form. It's not going away, it's not ceasing, it's not coming into existence. It's just changing into a new form. And a way to fundamentally, or a simple way to just state this would be that whatever mass, the grams of whatever you put in has to equal the grams of whatever you get out. It changed its form, but it's still the same mass that you put in, it's the same mass that you get out. Then the law of definite proportions is that a substance that's the same, that's water, always has the same ratio of the elements that are in it. So for example, water is always H2O. There's always two hydrogens and one oxygen that make it up. Now, when Joseph Proust did this, he said that the mass ratio was always the same. He found that it was always 8 times as much mass of oxygen as there was mass of hydrogen, because hydrogen is much lighter than oxygen. So, but that's the basic idea, that ratio between those elements is always the same in a chemical compound, in water, for example. You're never going to find a water that has 3 hydrogens on it. It wouldn't be water. It would be something entirely different. Then John Dalton came up with the law of multiple proportions. He said, well, sometimes elements combine in different ways, but they make different compounds. So, like, for example, carbon monoxide and carbon dioxide are both compounds made from carbon and oxygen. But what he said is that you can have these multiple proportions, but they're always small number ratios. Like, for example, there's 1:1 in carbon monoxide, or 1:2 ratio in carbon dioxide. So you can have those different ratios, but they're all those small whole number ratios to make different compounds from the same elements. And this observation was actually what led him to formulate a comprehensive atomic theory for what actually is going on with the fundamental particles of those elements. So there was this basic discussion all along that time about, was there a smallest piece of an element? If you took gold and chopped it in half, you'd still have 2 smaller chunks of gold. And if you chopped it in half again, you'd have a smaller chunk of gold, and chopped it in half again, you'd have a smaller and smaller and smaller and smaller and smaller and smaller. But would you eventually get down to just one thing that was gold that if you couldn't chop in half? If you chopped it in half, it wouldn't be gold anymore. And the answer was yes. Eventually you get down to the smallest piece of an element, which we call, and John Dalton called, an atom. So that's the smallest piece of something that is gold. And any chunk of gold can be made up of more than one, at least, gold atoms to come together. So the fundamental tenets of his atomic theory, to say that there were these fundamental small particles that made up an element, he said that each element is composed of tiny indestructible particles called atoms. He thought that they could not be destroyed. They were indestructible, so a silver atom was always a silver atom. It could never be destroyed. It was always a silver atom. that all atoms of a given element have the same mass and other properties that are different from other elements, that atoms combine in simple whole number ratios to form molecules of compounds. That idea right there is his law of multiple proportions that we were just discussing on the previous page. And then he said that in a chemical reactions, atoms of one element don't change into any other element. They just change the way they're arranged. They just changed what other atoms they're attached to. And that's essentially like the law of conservation of mass. They're not changing into something else. They're not getting a different amount of mass. They're just sort of changing the way they're attached. And so the compound they're in looks a little different in a chemical reaction. So that idea got us down to that elements are made. We've now discovered all these elements. Elements are made of these tiny particles called atoms. But then we ask the question a little further. Well, what is an atom composed of? What is an atom made up of? What gives it its unique properties? So some of the fundamental discoveries along the way about what makes up an atom were done first by J.J. Thomson. So we're discovered the particles that make up an atom: protons, neutrons, and electrons. So the electron was discovered by J.J. Thomson. He designed this device, basically, that he just shot electrons. He just charged the end, so it gave one end a negative charge, one end a positive charge. And at some point noticed that there were, he called them cathode rays, that there were particles shooting through the gap in between, that he could see shooting through in between, that were smaller than an atom. And he called these cathode rays. Eventually we started calling them electrons. We realized that they were negatively charged because they flew from the negative surface to hit the positively charged surface. They were attracted to the positive electrode, so they must have been negatively charged. Robin Millikan then devised an experiment to determine how much charge did an electron have. And he did that with this really cleverly designed device where he shot in a mist of oil here to get these tiny, tiny, tiny particles of oil. And then as they fell down through this positively charged plate, it stole electrons from them. So they fell through the positively charged plate and then shot them with a beam of ionizing radiation to steal their electrons. And then as they would fall, they'd be sort of suspended in the electric field, and they would move toward the plate down here at a different rate. And from that, he could deduce what the minimum charge was on an electron. Because every oil drop, went back a slide. Every oil drop would have different charges depending on how many electrons were stolen from it. So you could just decide what the least common multiple into all of those different charges were, and that's the charge of one electron. So we discovered the electron, that there were these things moving around, but no one really knew what it was. Some people came up with this idea they called a plum pudding model of the atom, like an atom was just this gooey stuff, and the electrons were essentially chunks of negatively charged particles in all of that gooey stuff that made up an atom. Until Rutherford did design this experiment, and this gold foil experiment is one of the most elegant, brilliant experiments in the history of chemistry and physics. So what he did was he got a lead box, and he put in the lead box a radioactive substance that emits these alpha particles, which are tiny, just the nucleus of a helium atom, 2 protons and 2 electrons. So those are going to be shooting out of this lead box. And what happened was he put a gold foil, which you can pound gold really, really, really thin, and that's what you call a gold foil. So he put a gold foil in the middle where the alpha particles would be shooting at. And then around it, he put a detector that would basically just light up when an alpha particle hit it. So what he did then, or what he noticed, which was just absolutely incredible, was that the vast majority, about 98% of all of the alpha particles that flew out of there, flew right through the gold foil and hit the detector. That's it, just zip, right through, hit the detector. Not stopping at all, as if the gold wasn't even there. And this was an amazing discovery. So the idea was that most of the space occupied by an atom actually isn't gooey material, isn't anything at all. It's something that an alpha particle can fly right through. You can just zip right through the space of an atom because it's mostly full of empty space. That almost all of the mass of the atom is actually concentrated right here in the nucleus. That's where the protons and neutrons are located. So when he shot it through, most went through because most of the space of an atom is just empty space. Some were deflected at wide angles if they got close to the nucleus and were repelled. Others, if they got shot straight at the nucleus, were bounced back basically where they came from because you can't fly through the space of the nucleus. So it gave him an idea of how big the nucleus was versus the overall space of the atom. And it really defined our current nuclear, what we call the nuclear model of the atom, and the way we currently understand an atom to be, which is this, the nuclear model of the atom. We understand now that an atom is made up of protons and neutrons in the nucleus, and electrons that fly around outside